Okay, well, welcome everyone to the last session of the day. And we are joined by Trevor Matthews. He is the founder of Refrigeration Mentor. Thank you for joining us today, Trevor. Today, he's going to be speaking on understanding CO2 heat pumps. All right, you're good to go. Trevor, thank you very much for coming.
Awesome. Welcome everyone to this session. I'm super excited to have a conversation with you and talk a little bit about CO2 heat pumps and things that you should know and really understand from a design point to a technical technician point. A little bit about me. So, my name is Trevor Matthews. I've been in the refrigeration industry for almost 20 years now. I started out in supermarket refrigeration, so installing stores, servicing stores. Then I got into industrial gas fitting. So, I got a full gas license. I have a red seal refrigeration ticket. I traveled all around Canada doing refrigeration work. And I work with a company before I start Refrigeration Mentor called Copeland. Some of you may know them. I'm assuming a lot of you do, and I was their national trainer for a while. So I would train on all their compressor technology, electronics, as well as do all their CO2 training around Canada and as well as North America. And about 2 years ago, I started my own business called Refrigeration Mentor, which is a technical training organization. And what we do is we help teach and build technicians' skill level, their knowledge to get them to where they want to be. Get them to the point where they're feeling confident. They understand how to troubleshoot systems. They understand how to even design and engineer systems. So it's a lot of fun. I have, as you can see there, I have a YouTube channel, which I get a lot of great content. I have actually done something called CO2 Mondays for almost 80 weeks now, every week. There was a few weeks that I missed, but almost 80 weeks with experts from all around the world on CO2 because it is something that is growing globally. Even when I started learning about CO2 back in 2014, it was still kind of new because CO2 is not new to the world. Refrigeration been doing CO2 for hundreds of years. And now it's just kind of revitalized. And so what I've been doing is trying to find experts around the world that teach us on CO2 and different applications. And we're going to get into a little bit more of that as well as I'm on many different social media platforms. And I'm trying to share a lot of technical knowledge with different refrigeration professionals out there, from technicians to engineers to designers to manufacturers. And this is what we do on a day-to-day basis, is help people understand refrigeration inside and out. Okay, let's talk about CO2 and why CO2. Why would you see CO2 in a refrigeration or in a heat pump? Well, one of the biggest things, it's environmentally friendly. And what do I mean by that? Well, it has uh, zero ODP, which means ozone depletion. Back in the 80s, something was called the Montreal Protocol. Some of you may have heard of it, may have not. But basically, this was refrigerant gases that had chlorine in it. So CFCs. And what happened, it would start to make a hole in the ozone layer. And then scientists seen this. And then there was now a phase down and phase out of those. So this happened a long, long time ago. So a bunch of refrigerants like R12s and the 502s and start to get delisted and phased out. Fast forward a few decades later, in Europe, they started something called the F gas regulation. So the F gas they call theirs the HFC. So or synthetic refrigerants, I call them. So back in that was 2006 in Europe, they started now phasing down and phasing out more refrigerants because of global warming potential, GWP. And you're going to hear me say this a few times. And basically, what is happening now, as you can see, GWP of one Kigali Amendment. Kigali Amendment was an amendment to the Montreal Protocol saying that the refrigerants that we use in air conditioning systems, heat pumps, refrigeration systems, they have a high GWP, global warming potential, which is heating up the planet. So what they've done, and they've all these countries start to sign on to this amendment to say that they're going to reduce the amount of HFCs that they're going to be using. And this is where it evolved to where we are now here in Canada. There are rules and regulations on different refrigerants you can use in your systems, even in heat pump refrigeration applications. And we're going to see these regulations continue to change. CO2 has a GWP of one, where 410A, maybe a lot of you know of, has a GWP of like 20 over 2000. So I think it might be 2100. So it's it's a high GWP limit. So for every 1 pound of 410A released, you can release, say, equivalent would be 2,000 pounds of CO2. That's just an example. You don't want to release any refrigerant, not even CO2. But this is one of the things that happened in the industry, and it continues to change. CO2 is an A1 refrigerant. You're going to start hearing more in your different, depending on the application you work on, you're going to hear about A1s, A2Ls, A3. So A2Ls is a mildly flammable refrigerant, kind of like R32, if you ever heard of that refrigerant. That's actually a refrigerant that is in 410A, but they're mildly flammable now. So there's different rules and regulations when you use a refrigerant like that. And then you have A3s, which would be R290 or propane, which are flammable refrigerants. Where CO2 now is it's a non-flammable, non-toxic refrigerant. One of the cool things about CO2 that I've been learning over the last 6, 7, 8 years is that it has a really high transfer of heat. So it's a very high coefficient of performance, a lot of BTUs per pound, which gives it a lot of advantages when you're designing systems. So if you're working on systems or you're designing systems, you'll see that the pipes will be a lot smaller than the systems that you normally work on because you can move more heat. And that's really what a heat pump is. We're going to dive into that. You're moving heat to a different place. And when I start to think about refrigeration or heating with refrigerants, it's movement of heat. I used to think, oh, refrigeration is cooling things down. Actually, no, it's the removal of heat. And it's no different when we're talking about heating a room. We're actually taking the heat from the outdoors and putting it inside your building or in your house. And one of the other things about CO2 is very inexpensive to buy to put in a system. This is actually some cylinders that you would get, depending on the size of application will depend on the size of the tanks you work on. So some of the terminology that I really believe is super important for anyone that wants to learn about CO2 as a refrigerant. The first thing is its number is R744. I got an image up here of Danfoss, good friends at Danfoss there. This is their cool Selector 2 app, really cool. This is a pressure enthalpy diagram. So if you haven't seen one of those in a long time, maybe from school or way back, this is what a lot of people, everybody's using for CO2. Like if designers, engineers, to get a good understanding on how heat is being transferred with this refrigerant. Even with CO2 heat pumps, to get a good understanding is you want to understand its enthalpy diagram. There's also a few terms that you're going to hear over and over again in CO2 with CO2 as a refrigerant, even in a heat pump. Something called a critical point. This is the difference between CO2 or R744 as a refrigerant than what you're working on today, like 410A. If you used to work on R22, and the different newer refrigerants, even A2Ls like the R32s or the 454Bs, is that every refrigerant has a critical point, but CO2 has a very low critical point. And what does that really mean, the critical point? Well, when you get above the temperature and pressure of the refrigerant, the critical temperature and the critical pressure, you're above the critical point. Now, this refrigerant is supercritical. And what does that really mean, Trevor? Well, that means that it's not a vapor, it's not a liquid, it's a fluid now. When you're above the critical point, you can see right here, when you're above this point, your system is running in there. You don't see this stuff, but when you're running there, this means that you're in that supercritical zone. So there's no pressure temperature relationship. And that's the big difference about CO2. And this is where heat pumps come into play. This is the zone you're running in for heat pumps. This is where you're gaining a ton of heat for the system. CO2 by far has the best characteristics for heat. I looked at tons of numbers from different manufacturers and tons of refrigerants, and CO2 can get some of the hottest water from a system. It's amazing how hot it can go, but there are design conditions which we're going to talk about. So as you can see there, when the ambient temperature is above 87.8 or 31 degrees Celsius and the pressure is above 1055 psi or 72.8 bar gauge, that means you're above the critical point. Okay. And I know some of you are like, wow, that's 1,055 psi. That's a lot. But think about the transition when, if so, I guess the older guys that were working on R22, and you're looking at, okay, the suction was 65 psi and 275. And then you go to 410A systems, and all of a sudden you're running at 120 suction and 420 discharge. Now, when you look at CO2, now they're going to be having higher numbers like that. So maybe double of what the 410A, maybe a little even higher than that, maybe even triple at some points, depending on the design of the system. So one thing you're going to hear is about CO2 is something called the transcritical cycle. And really what that means is that you're running above the critical point. And this is where CO2 heat pumps are going to be running, because you're getting a lot of heat at that point. You're getting a lot of heat to heat up that water or heat up that air, whatever the design of the system is. And we're going to talk about different designs from residential units, and we'll talk all the way up to commercial and industrial units. But you need to understand that. As well as there's something different, some other characteristics about CO2 as a refrigerant versus a synthetic or an HFC refrigerant. There's something called the triple point. So the triple point is where you have liquid, vapor, and solid. And that, so that what that means and what that causes is something called dry ice. So if I try to charge a system, and we'll talk about this a little bit later, you try to charge a system that you just evacuated down below 300 microns or zero point 0.3 torr, that means that you can't just add liquid at that point. Where we've been talking about for years, you're charging 410A or any refrigerant, we really want to charge with liquid. Any blended refrigerant, you wanted to charge with liquid always. But now, when we get into CO2 and you charge a system, you need to charge with vapor first. So you got to get above that triple point. So this is some uniquenesses about CO2 versus the refrigerants you're working on today. You just need to know a few of these things that really help you boost your knowledge, because a lot of the smaller systems, they're already charged. You're going to get them and you're going to just have to hook up your water supply, for an example. But when you get to a larger system, a larger heat pump, you'll be actually charging that system. Or if you had a leak on the system and you had to do a repair, there's certain steps that you need to take to charge that system. And we'll talk about that in a little bit. You don't want to trap CO2 unless you have the proper equipment. A lot of the heat pumps that you will work on, they have high standstill pressures, and really what that means, they can handle the pressures, so they don't blow any reliefs or anything. Where you'll see in larger commercial applications where there will be reliefs, you do not ever want to trap CO2, because the temperature can rise really rapid. If the system is designed for a high standstill pressure, then you're okay. So these are just some of the things that we talk about and we want to understand, because there are higher pressures and it's important to know these safety features. I talk a lot about the different units. I think this is really important. A lot of this equipment that you're seeing that is coming into Canada and North America come from different countries, come from Europe, come from Japan. And because CO2 is not new, and heat pumps and water heaters, CO2 are not new. So really the first ones that I've heard of was back in the late 90s. So they're called EcoCute. And they had, I think there's over 5 million of these CO2 water heaters in Japan. The government did some incentives. And so there's millions of them out there. So it's not new to the industry. It might be new to us, but it's definitely not new to the industry. And it's good to understand that, because people have been working on these for a long, long time. And where we just want to have a better understanding what is coming into the market. I'm not sure, has anybody, I'd love to see in the chat, has anybody been working on any CO2 heat pumps? Have they ever heard of CO2 heat pumps? Because there are a few here in North America that design CO2 heat pump water heaters, or water heaters, sorry. So 14.5 psi equals 1 bar. You should always know your units, because if you're getting equipment from Europe, it's going to be in bar a lot of the times. They're getting better and better at putting our local units on there, but you might see stuff in Celsius as well, because here in Canada we do PSI and Fahrenheit, but it may be You might get it in Celsius. So conversion 1.8 Fahrenheit to 1 Celsius, pretty straightforward for you guys and everybody on listening. Okay, so CO2 heat pump. This is a heat pump event. So I'm pretty sure a lot of you already know how heat pump works, but I just want to talk about what it is. If you understand refrigeration, you can understand heat pumps. It's basically refrigeration in reverse. So we're taking that condenser where we're usually rejecting the heat in refrigeration. If you work in refrigeration, where you're rejecting the heat outside, or even when you're talking about air conditioning, we're rejecting that heat outside. Instead of rejecting that heat outside, we're rejecting it in space, in the house, in the building, and we can take, even though the air is really cold, and I didn't understand this, like it took me a long time to start to realize this stuff, but even though you have really cold air, there's still heat in that air that we can use, that's usable heat that we can transfer indoors. And this is why heat pumps are growing immensely around Canada, immensely around the world, because of decarbonization, things called like electrification, if you ever heard of that. A lot of countries now are trying to decarbonize. They're trying to reduce the amount of fossil fuels being used, especially in Europe. I was in Europe a few times this year, and a lot of them had issues getting natural gas, and they want to start to reduce the amount of natural gas. Excuse me. And I even have manufacturers that I talk with where the end users want to stop the natural gas or the fossil fuels coming into their buildings altogether. They want to turn the supply off so they can go with heat pumps, heat pump technology. Because one of the big things is that heat pumps have a really high COP, coefficient of performance. And really what that means is that, like, for every kilowatt input equals your kilowatt output. Okay. So if you have, you're doing electric heat, 1 kilowatt in, it equals 1 kilowatt out. Now, with a heat pump, they could be up to 3 to 5 times better than, say, natural gas. And so that's what's the big uptake about heat pumps. You don't have to use as much energy to get the amount of work out of the systems. So you're really moving that heat from outside into the building. And it's so good it's really good to understand this. And I'm sure a lot of you already have been moving towards and seeing heat pumps, getting rid of electrical heaters or gas boilers. This is a big thing in the commercial industry, commercial buildings. They're looking for ways to reduce their carbon footprints and reduce the amount of gas that they're using, like boilers. I'm in Ontario right now. There's a ton of natural gas. I have a natural gas. I get central air and I have natural gas. One great thing about the natural gas, you get a lot of heat very quickly out there. And this is something that's going to have to be different in the industry. And you're going to need to understand, and even especially working with end users, is that you're not going to get the heat as quick with a heat pump versus, say, natural gas, because you got fire right there. You can really get it up quickly. You can heat things up like water heaters up really quickly. So it's going to be very important to understand the differences between, the boilers, the gas boilers versus the heat pumps, and this is something important. One thing about heat pumps, they work way better with, like, say, with lower water temperatures. So you have really cold water coming into the heat pump. You'll have really hot water getting out. One of the differences that I learned about CO2 is that you can get it up to like over almost like 190 degrees Fahrenheit or 90 Celsius. Really, really hot water you get out. We don't need that in our houses. We don't in our residential houses, but there are applications where they do, like, wash downs and stuff, and different processes where they need this hot water to clean their processes. And it's very important to understand that. But as we continue to evolve in our building envelopes evolve, even over the last 5 and 10 years, 20 years, the houses that we live in, the buildings were designed, they're being more efficient. We got better glass, we got better windows, we got better insulation. So we're going to see the evolution of heat pumps coming through, and we're going to see more and more of them installed. I talked to my friends out on the East Coast, and that's what they're putting in everywhere. Heat pumps are going all over the place because a lot of them still are running on oil burners. So, and that costs a lot of money. There's a lot of fossil fuels, and we're trying to reduce the amount of that stuff. So you're going to see a ton on the East Coast for sure, a lot of heat pumps. In Ontario, you're going to continue to see it evolve. Depending on where you're at, will be the depending on the uptake, because we have a lot of natural gas here versus somewhere on the East Coast, for an example. And as we continue to evolve our building envelopes, we're going to evolve technology like heat pumps. One of the things that I've been taught. So I got a couple of images here, right? So I've been doing a lot of talks, like I said, on CO2, and I've been talking to experts from all around the world. And for an example, how to integrate CO2 heat pump into a large facility. You're going to want to go check that out. If you're someone who owns a large facility or work in a large facility, it potentially could be a good opportunity. They're actually using the ocean water for that heat pump. So they're using that water to help maintain the building. And I believe it's an aquarium. I'll have to double check. It's been a while since I've seen that one, but they're using the ocean water, right? It's a great heat sink, and you can pull heat out of a lot of different things. You can pull it out of the air, you can pull it out of the water, you can pull it out of the ground. So to me, heat pump technology is really cool, but there's a lot of things you need to consider. We'll dive into that in a little bit, but you need to understand the thermodynamics of a heat pump. You need to understand that it works different than a refrigeration system, and you gotta understand a lot of the hydronic side. That's the big thing. I know Michael has been doing a session on here today, but the hydronic side of it, you need to understand the flow. How much is flowing? How fast is it flowing? And if you're a designer, this is critical to understand. A few of the other ones that I did one with Jean-Louis Paquette. So super cool guy. This guy's an industry legend. He has built and helped build the first transcritical high pressure low displacement screw compressor for CO2. So now this is large industrial applications, but this is going to be a game changer in the industrial industry. So if you ever heard of district heating, so district heating is where you're actually heating uh, residential areas, commercial areas with a centralized plant. So you're heating like whole cities, and we're going to see more and more of this district heating. There's a lot of it in Europe. There's even some here in Canada. I know I've done some talks with a few people who are doing and building district heating subdivisions, things like that. But that's a cool one. Talking about different technologies, a heat pump technology, and they actually built one with using that in a place in Quebec, in Hydro Quebec, where they've been running that heat pump now for I think over 15,000 hours. So it's pretty impressive what you can do with CO2 inside of a system. And they've been running that. I think that's maybe 4 or 5 years. And it's been going on for a while, running for a while. I did another one with ground source heat pump. I know there was another session with ground source heat pumps earlier today. I think it was just before this. And I had a good friend of mine, Parham, and he is a CO2 expert. This guy has been working with CO2 and CO2 heat pumps, and specifically ground source heat pumps, since I believe 2010, maybe even before that. So we did a session on it, and he was talking about direct expansion ground source heat pump. And he was telling me that right now, like at this point, and the studies that they've done, I think it was Camnet Energy that he was working for, this government entity, I believe. But he was saying that it was just so expensive to install like a ground source heat pump that it was, I think this is what he said, versus an air source heat pump. So an air source CO2 heat pump maybe take 4 to 5 years, we'll just say, on your ROI or your payback period, which is really good, The ground source heat pump is another 18 years on top of that. So that's like way too much. You can't do that. So they have to come up, and most of it was the installation cost. So he's actually come up with a technology. It's near the end of the video, where they use smaller pipes in vertical trains down into the boreholes. so you can put more pipes in the boreholes, which is really cool. So now this is reducing the cost because he really believes the direct expansion ground source heat pump is with CO2 is one of the most efficient systems out there, but we got to reduce the cost of those installation costs. And we'll dive into some of the technical stuff. And then the last one is a good buddy of mine, Daniel Clark from Sintra. He's out of the UK, but he's been designing heat pumps for over 10 or 15 years, more on the industrial and commercial side. But he designed big heat pumps using CO2 because the efficiency of the refrigerant. Not all systems you're going to want to design heat pumps with CO2. It all depends on the design. And if they're not designed properly, you're going to run into a lot of issues with this. One cool thing about all the people I talk about in the UK, they got a lot of the bugs out already. I know a ton of manufacturers here in North America who are building heat pumps now, working on them, going to be releasing them soon. Because I talked about the Kigali Amendment a little bit earlier, but I didn't really mention on the phase down and phase out. A lot of you might be using 410A right now, but because of the Kigali Amendment, what they're actually doing and what's actually happened is the reduction of the production of HFCs. And so what does that mean? Every year there's a percentage drop, or every couple years, and it's going from 90% production to 60% to 40%. So they're cutting the amount of refrigerants being produced. So that means the prices are going to start to skyrocket up. And in January 1st, 2025, that you can't even use 410A in chiller applications. So any of you working in any of the chiller type application, which puts a lot of pressure on the contractor, the technician, as well as the homeowners or the business is that have that type of refrigerant in their thing. So you want to start thinking ahead about this. I know it might not be in your realm right now if you're a technician out there and you're just working in the field, but this is something that you want to educate yourself as well as educate your customers as well as your company, because a lot of changes are happening. Here's one really good example. In California, for example, they stopped, and I don't know if it's a law, but there's no more gas boilers. So it's called electrification. So you can't have any natural gas boilers. So in the state, so now all of a sudden, what do? So now they're gonna start to go to heat pump. You're gonna see a massive influx of heat pump, especially when the US starts to change some of their rules and regulation. We all know it affects us here in Canada. It's been going on in Europe for years and years. We really need to learn what they are doing. I know here in Canada, our energy is a lot cheaper than what it is in Europe, but we need to learn from what they have done over the last 10 or 15 years and implement a lot here, because this is what I'm seeing. I'm seeing a lot of European companies coming into North America, bringing that technology that is further ahead here. There are things that you always have to look at. Depending on the system will depend on the design and your needs. So you always want to work with your customer to make sure, is this the right design for for their design, which is pretty cool. Let's keep going here. So CO2 heat pump for designers. Okay, so I've been learning. I'm not a designer myself, but honestly, I do a lot of design training. I do a lot of engineering training because I'm learning it, and I have a few partners in different businesses that I run. But in the design of a CO2 heat pump, Daniel was mentioning to me that some of the biggest things the designer needs to look out for is turbulence. You want to make sure there is no turbulence in those. In the buffer tanks. So the way the heat pump works, and sorry that I'm assuming that you guys know how heat pumps are designed. In the buffer tanks, you have cold water in the bottom, you have hot water in the top. Something called stratification. So what you want to do, if you have a lot of turbulence, it's going to mix up the hot water and cold water a lot more. So you want to be taking the cold water off the bottom. There's going to be like above it like 1 foot of kind of mix of the water, and then above that is hot water. But if you have a lot of turbulence, that's going to mix up and you're not going to have good quality water, because you want the coldest water as possible going into that heat pump, because you're going to get higher outlet temperature. So when you want to hit that 70 Celsius, 80 Celsius temperatures, You need the really cold water to go in. The next thing is flow rates. Differences in flow rates. So how fast that water is moving across those coilers or plate heat exchanger. You really want to understand that as a designer. And the pipe sizing. So any of you that are doing design, you want to understand this because making a mistake in the design will affect the efficiency of the system. And this goes for any heat pumps. If you don't design it properly, what is going to happen? That COP of 2, 3, 4, 5 is going to be reduced down quite a bit. And that's not what you want. You're doing this so you're getting more heat for less energy consumption. That's the whole point of heat pumps. So you got to think about that when you're designing. So any of you that are designing out there, think of those a few things. And then if you're a technician out there and you're working on these systems, a lot of the smaller systems, more residential, like commercial, these are already pre-charged. So the CO2 is already pre-charged in the system. You have to go through the installation process. You need to follow the instruction manuals of the manufacturer, and they're really good. Most of the manufacturers I've looked up, the ones that are selling here in North America as well as globally on, say, the residential side, the light commercial side, they have great installation manuals. It's our job as technicians to read them, to get a better understanding of how you really install those systems. But some of the things that you want to know, if you do have a leak on one of those systems, it all depends on where it's at. But if you have a leak on the pipe and you lose all the CO2, I talked about this a little bit earlier. This is one of the uniqueness of CO2. After you repair that leak and you pressure test the system, you follow proper pressure test procedures because you want to make sure you should be letting it sit there for 24 hours. I know lots of people don't do that. And you should make sure there's no leak for sure. And then you pull an evacuation down below 300 microns or zero point 0.3 torr, lower the better. And you want that to hold. When you go to charge this system now with CO2, you need the proper tools. You can't just use your regular gauges. You need hoses that can handle the pressure because inside a CO2 cylinder at room temperature, you're over 800 psi. Okay. So if it's a hot day out there, you could have 1,000 psi in that tank. The gauges you use today for your 410A would have the hoses are rated for 800 psi. If just say for an example, most of them are 8. I shouldn't talk for all of them, but a lot of them are 800 psi maximum working pressure, 4,000 psi burst pressure. So now out of that cylinder, you see a few images here. We have 1,000 psi. So you want to use a different rated hose. Okay, you want to make sure that you're using the proper tools. But before you put liquid into that, because now you got a good tight system, now you're going to add your charge in there. You need to add vapor first, like I said earlier. We need to get above that triple point. We're above that triple point. Say we put 100 psi or 150 psi or 10 bar of CO2 vapor. Then we put the liquid, and then we can start charging the liquid. On the smaller systems, it's very a small charge. But when you get to more of a larger commercial or industrial heat pump, that's where you could have hundreds of pounds of CO2, even thousands of pounds of CO2 in the system. So you really want to understand how it's done. But that's one of the things. You always need to be safe. Anytime you're working in refrigeration, air conditioning, be safe. You always want to go home to your family at night. You always want to get your job done efficiently, effectively, but you got to be wearing your safety glasses, the hard hat, gloves, boots, because you can get hurt easily in our industry. It is a skilled trade, so be safe out there. But this is one of the things. Here's another example right here. See, you get this little dip tube right here. It might be hard to see for some of you. Let me see if I can zoom in. See, there's a little, it shows a little dip tube kind of in there. Some of them will show you that, and that means there's a siphon in there. That goes down into the liquid. And then that would be a liquid cylinder. The other ones that don't show that, and say vapor cylinder, they don't have that dip tube. So that's the one you would use first. This one would be the one you would use second. But this one up here, one of my good friends, Steven, he sent me a picture. This guy's out of the UK. These are smaller tanks, but they're dual tanks. They'll have one that is vapor and then one that is liquid. Kind of like some of the things that I've seen in the past on cylinders. But that's a few things to understand as a designer and a technician. At the end of the day, if you're installing these, you really want to understand how the flow works, understand those hydronic side, and then controls. Controls is really any system today. If you're working on heat pumps, there's a lot of controls on heat pumps, on any refrigeration system. So you want to evolve yourself to understand how to work on those. You're going to be using more of your cell phone. You're going to be using more of laptops on systems today. Just get used to it. Embrace this technology because it's a lot of fun learning and growing from there because these systems are really cool to work on. So heating and cooling. So I want to throw this in there. I know this is a heat pump session, but I want to talk about heating with CO2 and the differences that I'm starting to see globally, even here in Canada, what CO2 is capable of in a system. So I was in Quebec a few months ago, probably it was quite a while now, back in March with some good friends from our NEG system. My good friend Philip Walker. We spent some time together. He has been teaching me a ton of CO2. But we went to one of his sites and he was like showing me what they've designed. And there's a lot of applications around the world, but what's really cool about this system here with CO2 does space heating, does water heating, does low temperature cooling, medium temperature cooling, and AC. And this is one of the differences with CO2 versus other refrigerants out there. You can do a lot with it with one system. I know this kind of looks complicated. You get some three-way valves, you got some stainless steel pipes there, but this is a larger system. So for those of you that are working commercial and industrial, these systems here, you just got to learn the process, learn the sequence of operation. This is any heat pump, any refrigeration system. When you learn that sequence of operation, when you learn how they work, that's a game changer for you because then you can go out and troubleshoot really anything at all. But it's taking the time to learn that stuff. And what I liked about this, I should have put a few more pictures in there. It shows the air handling units that it goes to, just like the air handling units you are using now. And that's the space heating. And then it's hooked up to a few of those are hooked up to plate heat exchangers. So where the water comes in and then that water goes back to the buffer tanks or the supply tanks. So really cool technologies happening with CO2. And I really enjoy seeing this because CO2 is starting to evolve all our industries, making people think a little bit more, thinking about the environment, thinking about how to design the system. Will it work better and more effectively than other things? So super cool for me, and I love talking about it. And this is a technology that's is going to continue to evolve and continue to grow, I believe, because a lot of people tell me it's like, oh well, Trevor, CO2 is inefficient when it's in warm ambient climates, so it's in warm areas. But that was 15, 20 years ago. Today, it's not the case. There's technologies out there that advance CO2, where now you add these different technologies and it makes CO2 systems more efficient. Is it different than HFC? For sure. But there's tons of CO2 water heaters, even here in North America. Like I said, there's millions of water heater heat pumps in different countries, millions and millions. So it's not new, but it's something important to understand. Okay, last thing. Last thing I want to talk about is skill enhancement. This is so important. I know today you come and you joined us, and hopefully you get to see a lot of the other presenters talk about heat pumps and their different designs. But for me, I'm all about training and development, from technical training to personal development. You got to put the work in. If you want to be the best at installing CO2 heat pumps, if you want to be the best at what you do in your career, you got to take training. You got to be continuing education from different virtual online, like this session here. You could be from all over the country, all over the world at this event right now. Go to in-person events. CMPX is coming up in March, I believe. So a little ways away, but start planning for that to attend an event like that. There's AHR that's before that. That's in the US, but that's another event where you can go meet and learn people. The top heat pump manufacturers from around the world will be at the AHR, and there'll be quite a few of them at the CMPX. Attend manufacturer training. You want to get better, you got to go to the manufacturers of the equipment you're working on. Hopefully they can help teach and educate you on the technical side, as well as if you're in the sales or project manager side, you can learn from them as well to help your customers to find out that solution. Is this the exact type of heat pump you needed for your commercial building or your place of business? Get it to expos. I talked about YouTube videos and podcasts. Start listening to them. Get your refrigeration heat pump acumen through listening and learning while you're driving to site, while you're driving to work. Learn about the the technologies you're working on, because this is how you grow. This is how you get better. You want to be really good at understanding heat pumps, especially CO2 heat pumps. Get to the Refrigeration Mentor CO2 channel and just go check all like 4 or 5 different heat pumps from experts. Not even me, from experts around the world. I'm just trying to share this knowledge to people like just like you, so you get a better understanding, so you're better at your job, and you can grow a lot faster. Last thing, if you guys have any questions, you can reach out to me, info@refrigerationmentor.com. You can see I'm on tons of different social media platforms. I'm here to help. If you want to get into technical training programs, if you're with a company, you're a technical company, or a contractor, and you're looking for technical training, reach out to me. I can see if I can design a course for you, because this is what we do. We design curriculum and courses for contractors and all around the country. So hopefully you learn 1 or 2 things. And yeah, reach out if you ever have any questions.
Thank you so much, Trevor. That was fantastic. Currently, we have no questions, but we have some more time. So there are 22 people of you guys sitting in the chat in the grouping right now. So do any of you guys have any questions? Now's the time to answer. I mean, you have Trevor's contact information. You can follow up with it following, but this is an ideal look at time. I'm going to give you guys a few more seconds. I still don't see any. All right.
Shane, what's up? I see Shane there. Sam, how you doing? Oh, I know some of the people here.
You're looking through the peoples?
Yeah.
You're going to start calling on you guys.
Yeah, call them out. That's what you do, right?
Yeah, I like that.
I don't know. I might know a few other of them. I'm just not recognizing some of the names. So
awesome. There we go. We got one that started to put the pressure on. Awesome. Thank you, Andrew. So if you're not a typical refrigeration, if they're not a typical refrigeration cycle, how do they work?
Oh, okay. That's a great question. If not the typical refrigeration cycle, think of refrigeration backwards. That's it. So it's the opposite direction. So instead of your condenser rejecting the heat outside, it's rejecting the heat inside. So it works the same way, just in reverse.
All right. Thanks, Trevor. You got a couple of shout outs as well that people are appreciating being called out in the grouping. So Shane saying hello.
Awesome. Good people.
Awesome. I've not met one bad person in our industry, so I can only imagine everyone here is good company. Okay, so we don't have any other questions. We can wrap it up a little bit early.
Yeah. Okay. Awesome. Yeah. Check out the podcast, check out the YouTube channel.
Absolutely.
Grow your knowledge.
Wonderful. Okay. So I do actually already know the other session has already actually just finished as well. So we're kind of timed perfectly. So we do have to still announce our winner of our big grand prize, which we will do in the closing remarks section. So everybody would have to go off of this call and then go into the regular sessions and go to the closing remarks one and join like you've been doing all day. So we will announce the winner there. Otherwise, thank you so much, Trevor, again. And thank you all for joining in.
See you later.